The atomic model did not just develop overnight. It's been a long time coming, and it's been changing and changing each time a scientist knows a little bit about it, and then the next one comes and adds a little bit more. And over time, we've developed the atomic model that we have today. Is it 100% right? Probably not. And each time the scientist was a little bit right and a little bit wrong. And so we developed on what we knew to be correct. It all kind of started with a man named Democritus, who was a Greek philosopher in 400 BC, and he actually gave us the word atomos, the word atom that comes from the word atomos, which means uncuttable, because he had this idea that if you could take anything and you just cut it and cut it and cut it and cut it and cut it, there would be a point to where you couldn't cut it anymore. Thus the term atomos, which means uncuttable. But we now know that you can cut the atom. We split it. It's called fission. And but then if you split it, it's no longer what it was before. It becomes something totally different. So the word atomos comes from uncuttable, which really is not 100% true today because we do split the atom. I want you to look into your book and read about the history of the atom from Democritus to the electron cloud model, which is what we use today. And it has changed. Each one of them added something to the model, and it changed over time to the one that we use today, which is called the electron cloud model. And once again, it could be that it changes again in the next 10 years. We cannot see the atom, so we don't know that it looks exactly like we think it looks. What we do know is what's happened to it on the outside. When we do things to it, we look at what happens on the outside, like in response to what we do to it, and that's called indirect observation. For instance, if I had a box and I put a bunch of stuff in it and closed it up, just everyday objects, pencils, pens, scissors, and closed it up, and I gave it to you and I said, "What's in this box?" What would you do to it? Well, you would shake it around, you might flip it over, you might bang on it, there'd be things that you can do the outside. You can't look inside it. So you might be able to figure out what some of them are, but you might not be able. Might not know all of it. So indirect observation just means you're doing stuff to the outside and trying to figure out because you can't see it. So you develop that model based upon that. The mass in the nucleus, the majority of the mass is contained inside the nucleus. That's where the protons and the neutrons are. One proton has a mass of about 1.66 times 10 to the negative 24th grams. Negative 24th, that's like a bunch of zeros. Okay, so it's super, super, super small mass. However, the mass of a proton and the mass of a neutron are roughly equal. And since they're so small, 1.66 times 10 to the negative 24th grams, they call it 1 AMU, 1 atomic mass unit. 1 atomic mass unit, because it's so small. Now, the thing about this is that a proton and a neutron are about 2,000 times the mass of an electron. So it just goes to show that the majority of the mass is in the nucleus, and that the electrons have very, very little mass. They call it negligible. Like, we don't even consider it too much because it's compared to the protons and the neutrons, it's very little mass on the electrons. All right? And so you can answer these questions. Which has more mass, an electron or a proton? Obviously a proton, 2,000 times more. Which one has more mass, a proton or a neutron? They are roughly the same. They are roughly the same, 1 AMU. All right, the size of the atom. This is a lovely little atom I've drawn. But when we talk about size of the atom, a good analogy that I was told once was, if the atom was the size of Yankee Stadium, The nucleus would be the size of a baseball. That's how small the nucleus is. A lot of time, compared to the atom, a lot of times we draw it kind of big so we can put stuff in it. But if you had one this size, then the nucleus would be very, very small, just like that in the middle. So the majority of the atom, size-wise, is the electron cloud. Mass number is essentially the number of protons and the number of neutrons in the nucleus of one atom. Now, this is an important number because this is how we get the number of neutrons in a particular atom. We can get the protons because that's the atomic number. And we can get the electrons because typically the electrons in a neutral atom are equal to the number of protons. Now, if it's not neutral, if it's charged, that changes the number of electrons. But we're going to assume that for the most part, they're neutral unless we're told otherwise. And that means the protons will be equal to the electrons. Okay, if you look down below here, this is the name of the isotope, magnesium 25. This number right here is the mass number. Make sure you circle that and you write that that is the mass number, because the mass number tells us the number of protons and neutrons. So I know a couple of things about this now. I know that it's magnesium, so the atomic number of magnesium is 12, so I know it has 12 protons. And I also know that it has 25 protons and neutrons together. So if I take 25 and minus 12, I'm left with 13 neutrons. Same thing here with carbon. Carbon has 6 protons. How do I know that? Because I looked at the atomic number. And then the mass number is carbon 13, is 13. So that means that that's the number of protons and neutrons together. So 13 minus 6 means that I have 7 neutrons. Potassium, I think, is 19 atomic number, so it has 19 protons. And as 36 is its mass number, so that means the number of protons and neutrons together. So if I take 36 and minus 19, that will give me the number of neutrons.